All right, so impedance, RLC elements, right? We are starting with purely resistive circuit. What this means is that the circuit only has a resistor, right? That's what we mean by purely resistive circuit, right? And then we said the basic equation is equal to V is equal to IR, and this based on this Ohm's law, right? And then the only element that's causing the resistance to the flow of the current is the resistor, right? Resistor. That's why we say it's a purely resistive circuit, right? For this particular one, because we are dealing with AC and then we're trying to find instantaneous, we write this as small v, small I, and then we have a capital R, right? And then we say these ones are functions of time, right? And then we are saying that for a purely resistive circuit, right, the voltage and the current across the resistor are in phase, right? They are in phase. Right, so if we are drawing their phases, it will appear something of this sort, right? So the voltage across the resistor, the current across the resistor are in phase, right? Okay, so this means that if you have, let's say, the voltage across the resistors to be something like this, let's say the peak, now the sign, right? We've seen this one already. This is a general of writing the sinusoidal quantities, right? The angular frequency time plus or minus phase angle, right? Then the current to be the same way. This is instantaneous, meaning they're the function of time. Or at a particular time, we can find the value, be given the values, right? Sorry. Right. So this says that if you write the equation for them will be similar, right? Because they are in phase. What phase? All right. They are in phase. Okay. So for this, for a purely resistive circuit, there's only what's the name? There's only one equation that basically describes the whole thing, right? And that's this one right here, right? So this for a purely resistive circuit, the current and the voltage are in phase, right? All right. And now we move on to another one. We have a purely inductive circuit. You can check the discussion if you haven't. What we said about this is that the voltage and the current are not in phase, right? A purely resistive, inductive, right, circuit. This means that there's only an inductor in the circuit, right? And then we said that the voltage and currents are not in phase, right? Which one is leading, which one is lagging? So we got to know that, you can check that. We got to know that for a purely inductive, the voltage leads the current by 90 degrees, right? So the voltage leads the current by 90 degrees, right? So voltage, current, as we can see, the purple and the yellow, right? And then for this one, there are two equations that actually describes it, right? So we have the one, so we started with V is equal to IR. This is the basic equation, right? Because we have only a resistor. But if it comes and we have a circuit where we have only an inductor, purely inductive, right? So that one we have V, right? And then we have I, and we have something like XL, which we saw this one to be this XL here, right? Reactance, but it's inductive reactance, right? Inductive reactance. And we've already gone over this already, but we're going to solve an example to see what happens with it, right? But then for this one, purely inductive, two equations describe the whole thing. So this is one, where we have a parameter of the inductor. So there's an inductor here, right? So we have the parameter of the inductor, which is this XL, and then we have another equation which has a parameter from the inductor, right? Which also contributes to all this, right? So what we've seen is that the what's the name? The equation for that one is this, similar to the V is equal to IR, but let's see. So we have small v, right? And then we have di dt, right? And then we have the parameter from the inductor, which is L, so capital L, right? Capital L. And then again, we'll have a way to go over this so that you get to understand. We are not going over the details of the explanations. We're just getting ourselves familiar with the equations, right? But if you want to check it out, fine. It will be very helpful. But then we are just going over what we've seen so far to make our computations with them easy, right? So we know for the purely inductive circuit, two equations describe them. Either this, which is similar to V is equal to IR, then or this, which also has a similar structure to V is equal to IR, right? But this only for purely what purely inductive, right? And we've seen that which one is leading, the voltage is leading. So if we have let's see. Now let's continue with this particular one. We are still talking about this one. So now this one is clear. We've done that already. Okay. So we know clearly that the voltage is leading, right? So if we have let's see, the voltage is leading, so that will mean that the voltage will be something of this structure, right? So we have Vm, we have sine, right? And then we have Wt. Anything could be here, any value integer will be here, plus 90. Right? This will mean that the current to be of will lag, right? So it will lag by 190, which we've seen here in this diagram here, very clear, right? Using their phasors. This for a purely inductive circuit, right? So we have I minutes. So you have Im, then you have sine, you have this, that's all, right? The only difference is that this one leads this by 90. The voltage leads the current by 90 degrees, right? Okay. A minute. By 90 degrees. All right. But then, we are not done with this. This is what I'm going to say. Because it's not always that you'll be given the parameters for this one. At times you might be given this, you might we actually play around it, right? So let's see, what's the name? There's another way to go about this. So that's how it is. So we have V is equal to I, it's not 4I, the I, the T, right? And then we have what? The L, right? What this means is that if you are trying to get it, we have V, right? This is a derivative. So we know that the current is of this sort, right? It lags, right? Okay. So then if we find the derivative of that, we actually end up getting Im, right? That's this constant out there. We are doing the derivative. This out, right? And what do you have again? So basically the function that we are finding derivative, there's a constant, so it's this one in here, right? So what will happen is that we will get, this could be, this number here is a constant, this one here could be anything. You have that, and then you have this Wt here, right? Right. Let's see. This one is the one that we find derivative of. Yep. So these ones are constant, so that's why we brought them out. These two here. So we brought them out, right? And when we get on the inside, will be cos, right? Then we will have this, and then this, right? So this is just for the I. This is just for the I. So is this that we found a derivative and it's giving us just this side, right? The whole of this, still the derivative, right? Still the derivative, right? Okay. So now that we've, so basically is this, and then we have this now. All this is I, right? Okay. So the only thing that's missing in this equation here is the L. So as I was saying, it depends on what you are given. So if you're actually given the actual I of V or something, you can find a derivative, right? And you get something that you can compute, right? Or you can punch in a calculator or something. Yeah. So that's what we have. Okay. So now that we have this, because most of them are in sine wave, we find a way to actually represent the whole thing in sine, right? So it's still the same. We end up getting V. Let's see. We have V, right? And then we have Im, right? And then we have this, and then this, right? And if we are changing this to sine, what do we know? Per the graphs, let's see. Let's go over this one more time. If you have this, right? Sine starts from the origin, right? And it goes this way, right? But then cos starts just like here. So what this means is that, then again, I'm doing freehand, so the graph might not be accurate, but we get to see what's happening. Okay, so what this means is that the, what do you call it? So this is cos, the brown one is cos, the blue one is sine. So you see that the cos peaks before the blue, right? So this means that the cos is leading the sine by 90, right? Cos lead the sine by 90. If we are trying to, so this means that if we are trying to change this cos here to a sine to make everything consistent, what we do is that we just add up a 90 so that the sine is able to catch up with the cos, right? So it comes like this, T plus 90 degrees, right? And then the L, right? So that's it. The same equation written in a different way, but it's still representing the same thing, right? Still representing the same thing. So that's it for this particular one. Okay, and now we move on to a purely capacitive, right? A purely capacitive. Minutes. Respondent. I get confused with these terms, whether purely capacitive or capacitive. Okay. This means that the circuit only has a capacitor, right? And what we've seen so far is that for something like this, what happens? The voltage lags the current by 90 degrees, right? Yeah, lags the voltage by 90 degrees. So we have 90 degrees, right? And then this again too has two equations for representing it. So the first one is we have similar to the V is equal to, so let's write it here so we have a reference. We aren't talking about this though, but just for reference. So we have cancel here. So okay. Okay. Minutes. Okay. So for this one, what we have is that we have a V, right? And the I, right? Let's write it properly. This one here will be, oh, this one will be, because you're taking it through the capacitor or through this element, right? And then we have what X. Oh, this capacitor. That should be C. Okay. And we've talked about this on the right, right? The other equation that help us to talk about what's happening in the capacitor is that we have this. Let's see, similar to V is equal to I, but there's a slight difference. Okay, so what happens is this one is that we have I as a function of time, right? And then we have the V, the T, right? And then we have the C, right? So we'll go over this one more time to see what's happening. So let's see. When you look at this particular one, right? Which one is lagging? The voltage is the one lagging, so we have a derivative of voltage, right, with respect to time. All right. So let's see. Then again, we are seeing which one is lagging. The voltage is the one lagging, right? So then, if we have it this way, we know the voltage is. If we want to do something with V is equal to IR, or if we want to do with some, let's see. Let's see. So V C is equal to I C, and then we have something like XC, right? So we're going to do something similar to this one, and then we have so now we are talking about the derivative one. So if we have the current, right? Which one is leading? So the current equation will be something of this sort. A minute. Okay, we have peak, right? We have sine, right? This is a general formula, right? The general way of writing it, right? So basically, what this means is that the current will be the reference here, right? The current will be the reference. Let me just confirm something. The current will be the reference, right? So if the current is being the reference, you can use a minus for the other, but let's say we use a plus for here, it's leading, right? This will mean that we'll have a voltage of this sort. We have a VM, right? We have sine, this, and then that's all, right? And the only difference is that the current leads the voltage. Then again, this is for a purely capacitive, right? All right. But then if we choose to go on this way, that will mean that if we are finding our current, we have this, right? And then we have the derivative of the voltage, right? There's the voltage. If we find the derivative, what we have is you have a Vm, right? And you have this, right? And you have a cos, right? And then we have this, right? Still again, we are writing this one. This is what we are writing. We have the V derivative, which is this, and we found that, and this is all this, right? The next thing to put there will be just the C, right? Just a C. Okay. And then because everything is in sign, I want to represent everything in sign. One way to write this will be that we have I is equal to V M, and then we have this. Is this an integer? We have the angular frequency. You can even bring this one, the capacitance somewhere here, right? And that will be capacitor, and then we have sine, right? And put this, and then add the plus 90, right? These are all just ways of representing this, right? Just the same way. Find ways to represent the same thing, right? But then we're going to solve an example to see what's happening. That's just, by the way, I'm just going to go over minutes. Yeah, and then we've also talked about when these elements are in series, when they are in parallel and everything or something, right? So now we are going. Let's see, just one more thing. We've talked about this XC, and we said that it's equal to 1 on WC capacitor, angular frequency capacitance. You said this angular frequency, and we have 2 pi minutes. This angular frequency is 2 pi f, right? And then capacitance, right? Yeah. And a similar thing is for that, we have the same thing for the inductance, right? And that will be XL, right? And that will be just we have W angular frequency and the L, and we have that to be 2 pi f and then L. And to help us remember this, let's see. What we have is that this one is up, right? You see, this one is like a number. What do you call it? Is up. The denominator is 1, right? So it's at the top. This whole thing is at the top. And when you look at the phases, you see that the voltage is at the top, right? Okay. When you go to the capacitor, what you see is that it has been inverted, right? So basically, we have the 1 at the top, and we have the 2 pi fc at the bottom, right? You go to the phasor, you see the same thing. It has been inverted, right? Inverted at the side. Inverted at the side. The other thing that we want to see is that when it comes to this again, let's see. When it comes to phase, we can use the phases to remember a lot of things, a whole lot of things. So let's see. When you look at the phases very well, you get to see that which one is the one lagging. The one lagging is the voltage, right? The voltage. And as a way of looking at things, you actually see that in this equation here, the one that we are having the derivative of is the voltage, right? Yeah. Okay. And when you go to that of the inductor, when you go to that of the inductor, let's see. What is this? Right. We look at the phases. The one that is lagging, right, is the current, and as a result, the one that we have it being a derivative in the whole equation, the one that we have a derivative of it, right, is the current, right? These are just trends that you see. If you get familiar with, you can be able to know the equations that you're using or something, or to recall it if you don't have them around. So here we have an example. Impedance. We're just going to solve an example to see if we really understand what we've been doing so far. It makes everything clear. So a coil has a resistance 12 ohms, inductance 0.1 Henry, connected across this voltage source. The frequency is given. Note that to calculate to check the reactance, impedance, current, right, and the phase shift between the current and the voltage, right? So okay, let's go over this. We are going to break it down before we even do anything at all, right? So the first one, so most of the times when you have a problem like this, you have to look at the question and get what you understand it, right? So we're trying to understand the first, the calculations can come later, right? So what did they say? He said we are finding what reactance, right? And then we are aware that we have two types of reactance, right? So we have the XL and then we have our XC. So you have to ask which one in particular, right? But the question says it says a coil, right? The moment you say a coil, we know that it's an inductor, right? And then for that means that what we identify to be just the XL, right? And then someone asks why is it that the coil has a resistance and an inductance, right? The reason is that you see, generally if you look in the fuse, right? A fuse has just a straight wire like this, right? A straight wire inside it. So if this is the fuse, just a wire inside it. A minute. Let's clean this up. Okay. So if you have a fuse this way, you have only a straight wire inside it, right? Just a straight wire. That's a fuse. But if you actually get to see an inductor, right, what happens is that the inductor has a straight side, and has the inductor has a straight side and it has this side, the core side, and it has this. Right. So what it means is that it is this side, this particular side of the whole element has some sort of resistance, right? And this side here has an inductance. So that's what it means. But if it is not specified, just use what you are given. This is just, by the way, just for just understand what's happening, right? Okay. And then the resistance of this. So we know the unit of resistance is a minute. We know the unit of resistance is ohms, right? And then the inductance, the unit of it is Henry. So you see, whenever you see a H, that's Henry. It's connected across a voltage of 100. What do you call it? Voltage source. It has 100 volts, right? 100 volts, which would be kind of like the RMS, right? And then it has a frequency of 50 volts, right? Okay. So let's see. So yeah. So we've dealt with this, the reactance, right? So the impedance, right? This will mean that we know the impedance is something of this sort. Impedance, we are saying impedance because there is not only one element that causes the opposition to the current, right? So that will mean that impedance Z, right? Impedance Z will be dependent on what do you call it, resistance and what was the name? Capacitive inductance, right? And we know Z vector is equal to, let's make it this way. Okay, you know Z is equal to R, right? And then we have this, right? But then this one here, this capacitive, what do you call it, inductive reactance is a part of this, right? So what it means that if you are trying to find Z, right? Let's see, trying to find Z will be equal to square root. So if since they are vectors, let's write this stuff first. Z is equal to R squared plus X, which is reactance squared, right? Okay. Yeah, then know it's all impedance, right? Okay. And that's what I was asking for, just reactance, right? Okay. So let's see. And then what this will mean is that if you're trying to find Z will be equal to square root of R squared, and then we said this XL here is a part of the X, right? This XL here is a part of the X, right? So what this will mean is that you can skip to the calculation side if you are okay with it, understand it. What means that we have this, and then we generally, if we were to have some other element, would have been XL, right, minus XC, and then we square it. But then this circuit here has only what? Resistance and what? Inductance, right? So that means that the XC part goes away. This side goes away and becomes only this, right? So that's how we find the Z, right? So now we know how to go about the Z, all right? And the current, right? Okay, let's see. So when we started the whole, what do you call it, apply electricity, were like V is equal to IR, right? And then this happens when the only element opposing the flow of current is R, right? But if we have other element with the resistor, then we end up getting V is equal to what? IZ, right? And we know Z is this way, and then it has all these things inside, right? So how we find the current to be what? V on Z, right? Yeah. So we have that as well. And the phase shift. Okay, let's see this. The whole circuit is saying is that we have what? We have a resistor, and then we have an inductor, right? So what this will mean is that if you're trying to find the phase shift, let's see. A minute. Okay, let's put it here. Okay. So we know that if we're to be a resistor alone, this is how it would have been, right? We have had this here for resistor alone. But here's the case. What are we having? We're having an inductor as well. So what this will mean is that, let's see, we have a minute. What this will mean is that we also have another component that is not in line with this, right? Because we have an inductor. So let's see how that will go. I'm just trying to put a face there so we can see what's happening. Right. Okay. So the current is still here. The current will be in line with the resistor, right? So it's for both resistor and across the inductor as well, right? But this right here is the voltage across the inductor, right? So this voltage across inductor. All right, so we know this is 90, right? But I want the phase. Set the phase between the current and the what? Let's see, the current and apply voltage, right? So here we can see clearly that what's the name? The voltage that we'll be looking for won't be only for the inductor or the resistor, but it should be some kind of like a vector sum, right? So as a result, the voltage that we are looking for will appear somewhere here, right? So just V, the voltage for both of them. So let's see, to be V, which is this V that we're talking about here, right? Yeah. So then, if we are trying to find this angle or this phase shift, that which is about here, the only things that we can use to actually find the phase shift will be if we're able to find, it's either we're able to find what's the name? We're able to find this VL and then VR, or we're able to find, let's see, able to find XL. You use XL and then use R, right, to find what we are looking for. But then in this case here, the one that's easier to actually find will be the XL, right, and then the R. And so we'll get to see what's actually happening. So now let's solve it. Now we've seen what we need to solve this problem, right? So let's see. Okay. Then again, we do some of the things just to make sure we understand what we are doing and to see where we are going. But then if you are familiar with some of the things already, it doesn't hurt to skip some things. Okay, so you could have skipped the explanation part and just continue the discussion at the calculation aspect, right? So let's see. So now trying to find E. E is what? Reactance and impedance, right? Reactance and impedance. We know the equation that we're using for that one, right? Okay, so let's see. Let's solve step by step. E. Right. Reactance. And we know the reactant that we'll be looking for here is what? Inductive reactance. And we know that is there's this and L, which is the same as 2 pi F, right? L, right? So let's see. 2 pi constant. The frequency is what we identify from the source, which were, I think, 50 hertz. And so that's it. 50 hertz. 50 hertz. 50. Okay. Oh boy. All right. So 50 hertz. Right. So that's 50. And then what's the L, which is the Henry that we had? The inductor, I think 0 0.1. Yeah, 0 0.1 Henry. Right. So unit of inductor is Henry. So times 0 0.1. Right. So let's see what we have for that. We have 2 minutes. We have 2. We have pi. And what we have 50. 50. And then 0 0.1. 1 to 1. Okay, so that's 10 pi. So like, what does that give us? You press this SD and it gives us 31.4. Let's do 40p. 59. And this is XL, right? Let's see. 31 point. So that was initial 10 pi, right? 10 pi. So these are resistance, right? They have the same unit as the resistance, right? Because they are all doing what? Opposing the flow of current, right? So that's what we have for this. What does it say? So now we have the inductance, sorry, the reactance, specifically inductive reactance, and the next thing we find is the what? The impedance, right? So we know what we need to find the impedance, right? So the impedance, which we know is this, right? We find it by doing this. R squared, right? Plus what's the name? XL minus XC, because they are in series. There's a way of doing it for series alone. There's a way for doing it for parallel when they're in parallel. We have an example for that. We solve it, right? Square. But then there is no XC. the circuit has only what, a resistor and an inductor, right? So we should pay attention to this. Then again, this is for series, right? Okay, so now let's see. Whenever you are asked to find a problem, it's very convenient. It becomes easier if you find the equation, get to find the parameters that you need, and you find them, right? So we know R, we have, I think, was it 20? Let's see, 12. Okay. So 12 squared. What do we have here? So if, to be fair, we can just write 31.4159 minus 0 squared, right? Yeah, so that's it. So we'll have square root. When I'm punching this, I put everything there and put the values in later, so I don't miss anything. Okay, squared, and I put a minus here. That's how I do it. It makes my, so if I miss something, the calculator will just see error. So I have to know I've left something out. 12, and have what here? 31.4159, right? And here is 0. Not important, but I put it there just for me to see what I'm doing. So that's 33.62 dp, right? 6297. Also another something causing opposite to flow of current, right? Ohms, right? So now we are down E. What does B ask us to find? The problem. It says the current, right? The current. So if we are finding minutes. Okay. So if we are finding the current, here what happens? We are no longer using V is equal to IR. Why? Because the circuit is not purely resistive, right? And then neither are we using V. Sorry, let's do this. And neither are we using V is equal to, what's the name? IXL. We are not using this either. Why? Because it's not purely what, capacitive. Right? So what we are using is V is equal to what? I and Z. Right? We are finding I. That's V on Z. We know V already. We have the V. Let's see. That was 100, right? From the supply. So that's 100 volts on Z. We have Z to be 33.6297. 7 ohms, right? You don't need to write this unit there, but yeah. Okay. So let's see. We have 100 on 33.6297, right? 6297. Now what do we have? We have 2.9736 amperes current. The unit very important. The unit very important. If you miss the unit, we don't know what you're talking about, right? Okay. So current. So that's for B, right? So we are done with B as well. What the next thing? We need to completely solve the problem. So the phase shift, right? Phase shift. We know clearly that the whole circuit, if we are using what's the name? If we are using phases to represent them, will be something like this. Let's clean this up so we see what's happening. So if we are representing the whole circuit using phases, this is how it appears, right? Okay. This is how it appears, right? So the whole of the inductive part will be here. A minute. Something. Okay, the whole of the inductive part is here, and for that side we have the XL and then the VL, right? The current is here for both of them, and for the resistor we have the VR and the R here, right? Okay, so this is the whole thing for the circuit, right? So, and then the V that we'll have as a result of the sum, what do you call it, the whole voltage through it, which is the 100 that we are having, right? 100 volts. The 100 volts from the supply will be here. The vector of it will be here, right? Let's do this properly. Okay, that will be here. Yeah, so that's V minutes. Just correct this. So we are consistent. We see what's happening. So we are simplifying the whole circuit, right? In phases. Yeah. So we have it this way, volts, and then the Z2 as well, which was opposing the flow of the current in the circuit to be this, in line with the V. Actually, to be frank, it's in line with it, and that's the Z, which we have the value for it. Yeah. So there's the summary of the whole circuit using phases, right? And then we want the current. Sorry, the phase shift. So the only way we can find the phase shift, as we said, is either we use this and this, or we use this and this. So you look at what you have. What do we have? Do we have the V for L, V for V in the what do you call it, the voltage in the inductor, the voltage in the resistor? No. What we have is the XL and what XL as in the inductive reactance and the resistance. So we use that, right? So per the phases, yeah. So this is the phases. This is the simplification. So this tan theta here will be, it's either, as we said, it's either will be VL, right, on what VR, or right, we have what's the name, XL, yeah, or R, but we don't have these ones, right? We have this, we have these, so we use that, right? But let's see, the phase angle phase shifts that we are looking for, right? That will be tan inverse minutes. Okay. So this phase shift or the phase angle that we are looking for will be tan inverse of what? XL on R, right? And then we have these already. So let's see. That'll be tan inverse. We know XL. Let's see what's our XL. That's inductive reactance, right? So that's 31.4159. Right? And then we have our resistance 12. Yeah, 12. Yeah. So if we are trying to find that, let's see. Tan inverse, right? Okay. Then we have 31.31. 31.416, and we have 12, right? 12. Yeah. Okay. Yeah. Then again, the unit that you're doing is very, because you are dealing with degrees, make sure your calculator is in DEG, not rad, or not in GRE gradients, something, to degrees, right? So that gives us 69.0946, right? Degrees. Yeah. So that's it.